Reducing assembly complexity, reducing material usage, or weight reduction are three reasons why you might employ a generative design tool such as Topology Optimisation. Now, Topology Optimisation is a form finding process. It can start with a number of design rules or goals and then explores a number of possible permutations of a solution to find the best option. The product you see on the screen is a small pipe assembly made up of a number of components. We're going to use Topology Optimisation for designers inside of NX to come up with a new design. One that has far fewer components but is also lighter, but more importantly still maintains the design intent. So let's take a look at our optimization geometry and our original assembly side by side using the latest window management tools. So the part on the left contains all of the geometry that we're going to be using for our topology optimization. We have the design space, which is the volume in which the optimized geometry will reside within, and then the bores of the pipework modeled as solid bodies, each one having either some thickness or a keep in or keep out rule associated with them. Now, a material has already been assigned to the geometry, so let's take a look at the load cases. We have a couple of features that are fixed, and those are the top and bottom flanges. We also have some pressure forces associated with the internal bores. Now all that's left to do is to run the optimization itself against a mass target of 6 kilos in this case. So the optimization runs a number of different iterations to get to a result which is suitable based on the characteristics and rules that have been set. Once the optimization is completed, the last part of the process is to actually mesh the resultant body, which you can then see on the screen. As the resultant body is a facet, we can very quickly hide the solid bodies so that we get a better look at our shape. As the underlying technology for topology optimization is based on finite element analysis, we can also very quickly see the maximum displacement and maximum stress in our optimized part. One important factor I hope you've noticed is that we've achieved one of our original reasons for doing a topology optimization, and that is to reduce assembly complexity. We now only have one component as opposed to the 12 in our original design. Even though we have our optimized part, the final design is still not completed. There were areas of our original design that we did not include in our optimization, so we need to add those in. And to do this, we're going to use some convergent modeling. So the first thing we need to do is to convert the output facet body from the topology optimization into a convergent body. So we use the convert facet body command inside of the reverse engineering application. And we can also check to make sure that the topology we've got is correct. So as you can see here, by sectioning it, we can see that we've got a solid form. Now we can take a look at making the additions to the design that we need to. The area that we're going to concentrate on in this demonstration is the top flange. As you can see, there are a number of features that are in our original design, such as a groove and some fixing holes. And we're going to look to add those into our new optimized design. So the first thing we're going to do is to copy and paste some faces from our original design to our topology optimized design. We simply use the keyboard accelerators Ctrl V and Ctrl C to do this copy paste. So let's take a look at the groove first. We're going to reuse the copied faces from our original design. To make sure that they protrude outside of the topology optimized body, we're going to use the extend sheet command. And then we should use trim body to remove the material from our topology optimized part. There you can see our groove has now been included. Now let's take a look at the fixing holes in the flange. Again, we're going to utilize one of the copied faces from our original design, but this time we're going to use it to position the holes. One important aspect to note here is that in NX12 we can now directly apply a hole feature to a convergent body. And this is just one of several key enhancements to convergent modeling technology in NX12. So we continue to place the other three holes utilizing the arc center of the copied face from our original part. And then we apply these holes to the convergent body. So let's hide the copied face and we can get a good look at the 4 countersunk holes we've now included in our topology optimized design. The final area of our original flange that we need to include into our new topology optimized design is the chamfer that runs around the edge. Now, currently in NX we can't apply a chamfer directly to a convergent body. However, under the reverse engineering application we have a new polygon modeling environment that allows us to directly modify the underlying facet geometry. And typically this capability could only be found in specialized software dedicated solely to this type of modeling. So we activate the polygon modeling task environment and select the convergent body. You'll notice that it rolls back the history to a time before either the holes or the groove were included in our design. And we need to do this to allow us to modify the facet body directly. You will notice that the polygon modeling task environment includes commands both old and new. But it's the new ones that we're interested in, the ones that will allow us to directly affect the shape of the facet body. And the one that we'll take a look at is called create transition. Now there are 2 transition types, either flat or a round. One simulates a chamfer, the other a radius. We've also got the option to either have an open or closed boundary, and we're going to select a closed boundary in this instance because we want the flat to run around the complete profile of the flange. The size of the flat has already been input, and now we select around the profile that we want to transition. Notice that we get a preview, and when NX has enough information it completes the profile and adds in the transition. So there we have our chamfered flange. Now I did mention there were 2 types of transition. So let's take a look at the second type, the round. This is used when you want to modify the edge of a facet body to simulate a blend. Again, we go through a similar procedure as we did for the flat. And again you have the same option whether you want a closed or open boundary. In this case again we're going to go for the closed boundary, and again you get the preview. And as we select points around the periphery, it builds up the profile. We've also got the ability to dynamically drag the profile to make sure NX completes the command as we need it. And there we are. We now have a nice transition similar to a blend that's on the internal bore. So all that's left to do now is to exit the polygon modeling environment, and you'll notice that all of the downstream features such as the trim for the groove and the hole features update. This means that our convergent body is now a full citizen of a history-based approach to modeling. So to recap, you've seen how we're able to use topology optimization inside NX to reduce assembly complexity. You've then seen how we can use the new tools in convergent modeling to make modifications and additions to our optimized part. The finalized design could then be manufactured using traditional manufacturing techniques like casting, or if preferred we could use 3D printing to generate the model.